Hi there, 8th graders. This is Miss Prente here, and we are starting our unit on plate tectonics. So if you will take a look at your matrix and look at the first objective, which is to describe the historical development and evidence that supports the plate tectonic theory. Understand that the direction of convection currents in the mantle determine the type of plate boundary. So let's take a look at our first essential question, which is to list and explain the evidence that supports the theory of continental drift. Okay, so Alfred Wegener was a German scientist who theorized that the continents were all at one time completely together and that they have slowly drifted apart over the past 250 million years. He developed this theory in 1912 called the theory of continental drift. At one time, when these continents were considered together, they were called Pangaea. They were a large supercontinent. Evidence to support his theory includes coastline shape, the plant and animal fossils, and evidence of climate change. In the beginning, the scientific community rejected his theory because he could not explain the reason that this movement occurred. But in the 1960s, another scientist by the name of Harry Hess proposed seafloor spreading, which is the result of the moving tectonic plates. Okay, so let's take a further look at evidence. Okay, so Pangaea are what you see here in this picture, shapes of the continental coastlines, and continental means we're talking about specifically the land masses, led Wegener to believe that the continents once fit together like a puzzle. Now we know that through erosion and time that these pieces may not exactly fit together at this point, but at one time they were completely put together. The continents broke apart and very slowly moved to the current location where they are today, and this movement still continues. So if you would, just watch this quick video clip on Pangaea.
It looked like they're joined together at once.
When you look at a globe of the Earth, it is easy to think that our planet has always looked this way, that the continents and ocean basins are where they've always been and where they will always be. But if you examine the globe more closely, you may notice something curious. Some of the continents appear as if they may have been joined at one time. A good example of this are the coastlines of South America and Africa. When you compare them, you will find, with just a little bit of adjustment, that they match quite nicely, like pieces of a jigsaw puzzle. And see how the island of Madagascar slides next to Africa. The same goes for North America. Its eastern coastline fits nicely around portions of Africa. People have been noticing these kinds of shoreline similarities for a long time. In the early 1900s, German scientist Alfred Wegener believed that in the distant past, later determined to be about 200 million years ago, the continents had been joined in a single supercontinent Wegener called Pangaea, and then had split apart, moving ever so slowly around the globe until they reached their present-day positions. Wegener called his theory of moving continents continental drift, and he offered additional evidence in an attempt to prove his point. Wegener found fossils of nearly identical animals in both South America and Africa. Wegener believed the only way identical animals could be found on distant continents were if the continents had been joined at one time. Wegener also found plant fossils in cold Arctic regions where these plants could not grow today. Wegener believed the plants had grown there before the continents had drifted. Wegener was convinced the continents had drifted. The only problem, he could hardly convince anyone else. Other scientists needed more proof, and that wouldn't come until years later when scientists mapped the ocean floor.
Okay, so that just shows you a visual representation of how Pangaea and the theory of continental drift came about. So let's move on and look further at more evidence. Okay, so here we have fossil remains of plant and animals, which he's already mentioned in the previous video, have been found on different continents. This was additional evidence that supported Wegener that he used for his theory. Similar rock formations, mountain ranges, were also on different continents and also supported his theory. So if you will, just watch this video clip very quickly. Okay, so that sums up talking about the second piece of evidence from Alfred Wegener. Let's go ahead and take a look at the next piece of evidence, which is based on climate. Okay, a piece of evidence that Alfred Wegener discovered regarding climate changes was evidence of tropical climates were now found in polar regions. An example of that would be tropical fossils that were found in Antarctica. Evidence of polar climates in now what we would consider tropical regions was also found. Examples of that would be glacier scratches found in Africa, Australia, and India. All right, moving on to the next question on your WQS. What technology is used to map the seafloor? Let's take a look at seafloor spreading. Okay, seafloor spreading in the 1960s, this new sonar technology developed, which was referred to as sound navigation and ranging, was developed, and this was developed and helped support Alfred Wegener's theory of continental drift. It discovered the mid-ocean ridges were underwater mountain range and that the new ocean floor formed at the ridge and it got older as it moved toward the continental shores or towards the land. This process is now known to be driven by convection currents in the Earth's mantle. Okay, looking at the next question, what is seafloor spreading and how does it support the theory of plate tectonics? Let's take a further look at these convection currents and how they cause the seafloor to actually spread. All right. Convection currents are a cycle of warm magma rising and cold magma sinking in the mantle layer of the Earth, which drives the lithospheric plate movement. The direction of the convection cells determine the type of plate boundary. So if you look at the diagram here, you can see in the center is the core, inner core and outer core. The next level or layer of the Earth is the mantle, which you see here, and you can see it defined. You can see the oceanic lithospheric plate, which is this area here, which is just the lithosphere that is underneath the ocean. And then over here, the continental lithosphere, which is the part of the lithosphere that is underneath the land or part of the land. Here you can see the convection cells and the hot and cold magma in the mantle causing this upwelling. This upwelling, as you can see here, creates this seafloor to come up and spread apart. As you can see, the arrows moving from the left to the right, and that is what we refer to as seafloor spreading. So these convection currents that occur in the mantle underneath the oceanic lithospheric plate, as well as the continental lithospheric plate, causes the seafloor to spread. Okay, looking at plate tectonics, again, just to summarize, this is the modern day theory that the Earth is divided into 7 major plates. And you can see a picture here that's got those 7 major plates, and that these plates are in constant motion, again, driven by those convection currents that are in the mantle. So what are plates? Lithosphere, which is the crust, whether it's under the ocean or under the land, oceanic or continental, and rigid part of the upper mantle which floats on a partially molten asthenosphere layer. Convection currents in the asthenosphere control the direction of the plate movement. And you can see in the picture here, here's the mantle, this whole area is the mantle, and you can see the asthenosphere is this partially molten area. This lithospheric layer is a solid area. And you can see that this is the continent, which would be the land mass, and this is under the ocean. So that summarizes our idea of continental drift. Alfred Wegener's theory, how it's supported by seafloor spreading, and what layers make up the Earth, make up the lithosphere, and how convection currents move.